So let's get started. So today I'm going to introduce some of one of our recent works, which is about the reward-free exploration with function approximation. So I would like to spend like half of this presentation to introduce this setting, and try to use the remaining half of them to introduce our algorithms and to show why our approach is better. And if time allows, I will also show some of experimental results here. So this is joint work with Junkai, Wei Tong, and Quan Juan from UCLA. So overall, this work is about the offline reinforcement learning. So the previous two presentations today have introduced the very classical reinforcement learning setup, which is called by the online reinforcement learning. So we can just record the setup. Says at the beginning, our agent is trying to interact with an unknown environment, and the agent will decide how to interact with the environment and receive some of the feedbacks from the environment. And the goal for the agent is to try to find something called by the policy, which aims to maximize the cumulative return. So this setup is very classical, and a lot of the state-of-the-art application of the reinforcement learning like to use the RL to play the game like the StarCraft, or even to use the RL to build some kind of the chatbots. They all use more or less to use the online reinforcement learning. But the thing here is that one of the main drawbacks of the online reinforcement learning is that the agent needs to interact with the environment, and based on the interaction, the agent needs to update itself in the real time. So this kind of interaction is not allowed in some kind of cases where the interaction is too slow, or the efficiency is not that high. So in order to address this kind of issue, the offline reinforcement learning is proposed. So just unlike the online reinforcement learning, the offline reinforcement learning will try to decompose the so-called interaction with learning into the two disjoint parts. Says it aims to first collect the data and use the existing log data and to try to build some policies which still aims to maximize the cumulative return. So a lot of the works have tried to study the offline reinforcement learning setting, and here I just used the very interesting result from Chen Jiang, and their theorem suggests that even though offline reinforcement learning seems like can decompose the data collection phase and the learning phase into two disjoint phases, but here comes the prize. Says if we want to use some notation called by C star, which denotes the coverage of the ultimate policy of the given offline data set. So this coverage is just a very abstract definition, but in general, you can just regard this coverage as if I have some offline data sets, then in order to learn some of the policy, at least we need our data set can somehow describe the policy interaction between the agent and the environment. So they show that this kind of coverage of something called by C star is very essential to allow the offline reinforcement learning agent to learn the optimal policy. So this is actually different from the online reinforcement learning, because in the online setting, the agent has the freedom to interact with the environment just as whatever as it wants. So in order to address this kind of issue, and the main goal of this work is to try to find a way, try to collect the right data to enable the optimal policy learning, which essentially saying that we want to find a scheme to collect data from the environment, which ensures that the C star is more this kind of assumption holds for a lot of the different tasks. And in order to collect the right data, we have the two challenges. The first challenge is about the generalization property of this data collection scheme. So actually, the most typical way to collect the offline data if you have ever tried to do some experiments for the offline reinforcement learning, is that we can use some online reinforcement learning algorithms, for example, the soft actor critique, to interact with the environment. And during this interaction process, the online agents will try to find the optimal policy just due to the designing purpose of this reinforcement learning algorithm. And then, in the end, the agent will try to find the optimal policy, and we can just collect the offline data from its policy, from its replay buffer. So this is a very typical and useful strategy to collect the data. Its advantage is that it is guaranteed it can cover the optimal policy because the online agent can automatically find it. But the negative side here is that it needs to specific the task, or I can call it as a reward, in order to collect the specific data which is aligned to this optimal policy. So like we have the instances, if we want to use this SAC to collect some data, and it's very likely that if you just denote this kind of task is to try to move the robotics arms, then it can collect the data according to it. But if you want this kind of data to cover another task, for instance, to lift some cup or to move around, then it is very likely that this kind of data is unable to cover it because the task here is different. But in the practice, we want to collect the data which can cover as many different tasks as we want. So the first question here is that how can we design some kind of data collection scheme to collect the data which covers the multiple tasks simultaneously? And the second challenge here is due to the large state and action spaces. So if we, if suppose that the environment we are facing is very small, says it only has a finite number of the state and actions, and the number of state actions is very small. So in this kind of situation, we can build something called by the generative model. So this generative model is something that if we just put any kind of state action pair for the generative model, this model can return us some kind of the next state which is generated from this generative model. So this generative model since actually recently is really popular because like a lot of the recent breakthroughs like the large language model or the diffusion model, all of them actually are focusing on build some kind of generative model in order to describe the true dynamics of some complex environments. So the positive side for this kind of approach is that it works for evaluation for any of the policy and tasks, which means that as long as we get this kind of generative model, for any kind of tasks, we can always try to sample the desired state distribution, and we can utilize this empirical distribution in order to build our optimal policy according to this sample distribution. But the negative side here is that it is a model-based approach, and we need to put a lot of the efforts to design it in the empirical sites, and we also need to put a lot of the data samples in order to build this kind of thing in a very accurate way. And often we need to get some additional module like the planning module to really get this optimal policy if we only have the generative model here. So our next question here is that how to collect the good enough offline data even for the large state and action spaces. And here I want to use some recent work to show that even from the empirical sides, the exploratory offline data, well, I use this term like exploratory to try to summarize the property, including both the generalization and the large state and action space. So the recent work by Roberts suggests that if we already have a very offline data with the benign property, which just has the properties we described as the challenges in the previous slides, we do not need to use this kind of sophisticated designs offline reinforcement algorithms like the conservative Q-learning, like CQL, or the TD3 plus BC, this state-of-the-art offline reinforcement learning baselines. So if we already have this kind of good offline data, even if we use the very vanilla of online reinforcement learning agent with like the vanilla of policy algorithm like the TD3, it is able to achieve the good performance on the multiple tasks. Even this performance is compatible with the pure online reinforcement learning agent. So this again suggests that to collect the good offline data can dramatically help the final performance of the offline agent. So our work aims to make a further step in this direction. So we propose an algorithm called by the general function approximation assisted reward-free exploration. So this algorithm is built under the framework called by the intrinsic reward exploration framework. So I will try to introduce these details later. And for the general function approximation, we built some additional algorithm designs in order to estimate one module called by the uncertainty, which we will utilize them to further improve the data collection efficiency. And also employ this general function approximation into the policy learning. And we show that our framework is achieve the state-of-the-art sample complexity. Of course, the sample complexity is specified to the data collection sample complexity when specified to the simplified settings like the linear MDPs. And also our framework is computationally efficient, which means that you can implement them and it is totally runnable in the true experiments. Okay, so we can just proceed to the preliminary. And in order to show some of the details of our algorithms, we first need to specify to some specific environments we want to discuss. So here we just choose a very popular framework called by the timing homogeneous episodic MDP. So here, this MDP is episodic, and which means that we need to use like the number edge of the different policies in order to interact with the environment. So this environment here, we just assume that at each of the stage, the transition dynamic is actually different from each other. And here, we denote the rewards as another definition called by the task, which is again the H different reward functions, and we'll assume that the summation of the total rewards will always fall into the intervals between 0 and 1. So here are just some regular normalized assumptions in order to provide the standard framework in order for the further comparison between our algorithms and the previous ones. So just based on the reward function, we can just define the value function, Q function, and the Bellman backup as usual. But the thing here is that because here we want to study the generalization property, which means that we want our algorithm holds not only for one specific reward function, but also for the multiple different reward functions. So here we just give these definitions of the value functions or the Q functions or even the Bellman backup with the, we just take the rewards as their input. So the goal for this agent is still to find the optimal policy regarding to the given task-specific reward here. And because to find this optimal policy itself may be computational inefficient, so our goal is to try to find the absolute optimal policy, which is just defined as some policy the value function with respect to this policy is at most epsilon away from the optimal value. So the algorithm framework we introduced here is so-called by the intrinsic reward. So like I have mentioned, our algorithm actually has two different phases called by the exploration phase and the planning phase. So for the exploration phase, the agent is not given the reward or the task in this phase. So our agent wants to collect the data as uniform as possible, and it will collect the data for the use of the next planning phase. So we can describe this phase as at each of the step of this exploration phase. Suppose that currently this agent already collects the data set, already has the collected data set, which is denoted by H, and which is the union of the number H of the individual collected data sets. The agent will try to design something called by the intrinsic reward. So this reward, it has nothing to do with the true reward, which we will use in the planning phase for the agent to find a final optimal policy. So that is saying this intrinsic reward is something the agent needs to design it by itself. And after the intrinsic rewards is collected or decided by the agent, then the agent will obtain the policy, which is approximately the ultimate policy according to the intrinsic reward. So the agent then will run this near optimal policy with respect to the intrinsic reward and obtain the state and action and next state pairs from the interaction between self and the environment. And then the agent will try to add the newly collected data tuples into the collected data. And the agent will denote this intrinsic reward and the near optimal policy according to this intrinsic reward at each of the stage. And most important thing is that the agent needs to change or to update its intrinsic reward as long as this collected data set has already changed a lot. So this is something called by the exploration phase, because in the next slide we will see like the design principle of the intrinsic reward is that we want to use this reward to represent the uncertainty according to the unknown environments given the past experiments we have. So for the planning phase, the thing is much more simpler. Says in the planning phase, the agent has already collected enough data and in the data set H, and it is also given a true reward denoted by the reward R. So in the planning phase, the agent will try to relabel each of the state and action and the next state tuple inside each of the inside the data set, by extending it from the state action state pairs to the additional thing, which is labeled by the reward functions, which is revealed in the planning phase. So with this relabeled data set, the agent can obtain the optimal policy according to this data sets by running any existing like the off policy algorithms, because now it can actually plan from it. So that is the overall framework of our algorithm. And I want to give some additional comparison between our framework and some other frameworks, which also designed for the reward-free settings with the general function approximation. So to compare with the estimation to decision, this framework, which is first presented by Foster and laterly extended by Chen et al. So this framework will try to maintain the distribution, try to maintain a policy distribution over all the potential policies, and it will try to treat it as first learn the underlying model, then to pick some of the policies which is most likely to be the optimal one according to the learned model. So compared with their framework, our framework do not need to maintain a distribution over all the potential policies, because in real-world practice, it is often very hard to implement. And compared with the reward-free olive framework, which is also proposed by another chain or algorithm, the work. So for the reward-free olive, this framework, it will try to use the value function or the policy elimination approach, which again, they need to store all the possible value functions or the policy at the beginning of the algorithm. And then it will eliminate them based on some collected data samples, which could reveal like these values or policies are explicitly not optimal anymore. But again, this framework is hard to implement in practice because it's very, very hard to just maintain a collection of all the policies and all the values. So to compare with our framework, it's very likely to the classical reinforcement learning framework. The only thing here reminds us to reveal is that how do we design the intrinsic reward in order to guarantee both the generalization property and the efficiency issue. Okay, so next I will proceed to the algorithm part. Sorry, I guess I need to hash it a lot, but because I think the clock in the backward is stopped. Yeah. Okay. I just keep trying to dig in for that to see where am I, but okay. Okay, so let's try to hash it. So the algorithms we introduced here is based on the least square value iteration, which is a very popular framework originally designed for the reinforcement learning with the linear function approximation. So in general, suppose that the agent has an offline data set and the intrinsic reward. This LSVI will try to approximate the optimal value function according to the given reward by solving the regression problems defined based on the existing data set. So this one is this one actually needs to introduce the function class. Well, in the original linear MDP paper, they try to denote this function class just as a linear function class, which means that we just try to approximate the optimal Q function based by using some of the linear functions. And this framework is very powerful as it can provide us the probable efficient reinforcement learning algorithms for the with the linear function approximation. But here we want to extend it to a more general case. Says we do not only use the linear function class, but we just use some general enough function class, like either the kernel function or the neural network function, or even something more general. But we need some assumptions about the completeness. Says we want our general function class to be expressive enough. Says it can represent for any of the reward function and the value function, it can represent their Bellman backups as well as their second order momentum. So this is our starting point. Says we want to design our algorithm based on the LSVI framework. So the next two things we want to address is that how to denote the intrinsic reward. Because here we assume that we have already collected the intrinsic reward, and we know how to collect the approximation of the Q function, but we have already not introduced how to denote this intrinsic reward themselves. And the second thing is about the planning. Says how to learn the optimal policy from the existing data sets in an efficient way. So this just comes to a second key part of our algorithms called by the uncertainty estimator. So this originates from the uncertainty estimator from the supervised learning framework called by the episodic uncertainty or the allotropic uncertainty. So in the reinforcement learning, in the reinforcement learning context, we will try to denote the episodic uncertainty as uncertainty caused by the small numbers of the samples, which just makes our prediction of our constructed predictor not accurate enough. So here we just denote uncertainty as the difference between our constructed predictor, which is the head of FH, with its target value, which is the Bellman backup applied on the next stage optimal value function. So for the allotropic uncertainty, it's some uncertainty caused by the transition dynamic itself, which says that this uncertainty will be non-zero, even if you have plenty of the data, as long as the transition dynamic is not deterministic. So I will just skip these details. And based on these two introduced uncertainties, we will introduce something called by the weighted regression. So this weighted regression is some extension from the original LSVI. Says we introduce something called by the uncertainty aware weights, which we denoted as a W here. So this weight will just be constructed as the inverse of both the allotropic uncertainty and the epistemic uncertainty. So the whole idea is that we want the samples belonging to the existing data sets to contribute to the regression in a small proportion if this data itself has already been revealed to be very uncertain. So that's aligned to our intuition because we do not want some kind of very noisy example or some very low quality example to somehow to corrupt our regression target. So this is the key techniques has been adopted in the previous works. So for the intrinsic rewards, we will try to design this reward just try to set it as the epistemic uncertainty. So this reward will encourage the agent to explore the most uncertain direction given the existing collected experiences from the interactions. And our key lemma suggests that as long as we just choose our intrinsic reward in that way, we will have an inequality, says the suboptimality of our obtained policy based on the given data set can be bounded by the optimal value according to our intrinsic reward. So notice that this intrinsic reward will approach to 0 as long as this data set goes to infinity. So that suggests that as long as we just choose this intrinsic reward, we can guarantee that our obtained policy is near optimal. So for the theoretical guarantee, so our sum of complexity suggests that our results suggest that for any test the true reward function, our algorithm is guaranteed to return the absolute optimal policy after collecting the h squared times the covering number times the generalized Euler dimension, which is the dimension based on the classical Euler dimension with the additional definition of the weights, and with the standard epsilon to the negative square sum of complexity here. So this just improves the existing state-of-the-art results from both the dependence of the horizons and the dependence of the logarithm of the covering number. So when specified to linear MDP, it also matches the best results, and it still exists the H gap from the lower bounds. So how many times do I have? Okay. So our experiment suggests that we compare our algorithms on the continuous control task from the demand control suite. So here, we just utilize the two settings about the worker and quadruped. So we will compare our algorithms based on the 4 different tasks, like to train them to stand, to walk, to run, or to flip. And our comparison suggests that the GFA, the reward-free exploration algorithm, just returns the exploratory data at the same level as the state-of-the-art baselines. But just to mention that the previous baselines, they are all proposed from the very intuitive way, or even from the empirical side without the strong theoretical guarantees. And also notice from this comparison figure, it is noticeable that in the initial training steps of the offline planning, and our agent actually just suffers from the slow learning speed, and we claim that it is due to the additional, like the uncertainty-based weights we need to learn. And we also do some ablation studies, says what is the relation between the exploration episodes with the final return. So essentially speaking, it says that the more exploration we have, the higher return we have. And so the quality of the exploration of our algorithm is at the same level as the other knowledge-based intrinsic rewards. Okay, to summarize it, our algorithms can provide the state-of-the-art sum of complexity for collecting the data from the environment, and it is computation efficient, and it is also empirically sound. So we still have some open questions. The first one is try to close the gap between the upper and the lower bound, because it still exists like the H gap. And the second open question is that can we try to leverage this kind of idea just from the pure data collection scheme by extending it to some more realistic setting, like to mix. What if we can just combine both the offline learning and the online learning into one? And can we just try to extend it to the more specific setting, like the reinforcement learning from the human feedback or something else? So that's all. These are to discuss and to explore. Okay, thank you. Yeah, please. Yes, yes. So actually, we adapt the. That's something I skipped. We just utilize the backbone algorithms as the DDPG, which is you can just imagine it as a baseline, which is very similar to the value-based algorithm, but we just use a continuous policy in order to somehow to mimic these argmax operation if you just do the for the discrete space. Yeah. Okay, thanks.